part of physics. And the word relativity, what it basically means is this part, that is basically relative to something. Okay. Now, what do you mean by relative to something? It basically means that what I see may not be the thing which you see, or what I observe may not be the thing which you observe. Our information delays, our information changes, and it's not the same. So if you need to understand it more well, you can use these two words too, which is like POV or WRT, which means point of view or with respect to. Okay. Now we will go into detail into these two words later on, but before entering into relativity, one point which you need to remember very well is this one, that everyone is at rest with respect to themselves. Like everyone in this inertial frame of reference, in this inertial world, thinks that everybody is at rest with respect to themselves. So if you need a quick example of that, I have drawn a point A on Earth and a point B far away from Earth. So if you are at point A, with respect to you, you are not moving, you are at rest, because we don't feel anything when we are on Earth. We think that we are at constant rest. So when you are on Earth, you are actually moving at 460 meters per second, but you don't feel that because obviously of inertia. But when I see you from point B and you are standing at point A, I see you moving at 460 meters per second. So I would basically conclude from point B by looking at you at point A that you are moving at 460 meters per second, but you at point A would always say that you are at constant rest. So this information delay and this information not matching between two frames of reference, this is what relativity is going to be. So now we are going to enter Galilean transformation equations, which is basically an overview of only the Newtonian world for now. I mean, you would enter the interesting part later, but this is basically what happens and what we see in our daily lives. That is what is explained by Galilean transformation equations. So before entering into Galilean transformation equations, there are two assumptions which you need to make. Okay, first is that this line you can read, space is homogeneous and isotropic. So what do you even mean by that? What is homogeneity, or what do you mean by homogeneous and isotropic? Okay, so you know the laws of physics work on Earth. So how are you sure that the laws of physics will be the same and will also work in somewhere, say in the Andromeda galaxy? So this is what we know, that it is also the same in there, and that is what homogeneous and isotropic means. Homogeneity basically means that the universe doesn't have any particular direction to go. Are we at the center of the universe? I mean, I don't know, maybe we are, but for us we are, maybe for others we are not. That is what is explained by homogeneity. It is that the universe is so uniformly distributed that everywhere you look around is the same and uniformly distributed everywhere. That is what is explained by space as homogeneous and isotropic. So it is viable everywhere in a normal rate of speed. And this one is a bit controversial, but for now you can assume that t dash is equal to t. I mean, for now. So basically, what is this t prime? Okay, this symbol, this apostrophe symbol which you see on the top is called prime, which basically means, suppose you can take that as me. T prime is me and t is you. Now we all know that t is time. So I mean, it somewhat makes sense to say that 1 second for you will also be 1 second for me. I mean, for now it makes sense. Suppose the bell is going to ring in 5 minutes, the bell is going to ring in 5 minutes for me, and it also will be ringing in 5 minutes for you. So for now we can assume that t prime is equal to t. Now we are going to move to frames of reference. Yeah. So now we are going to do the derivations of Galilean transformation equation. Now very simple derivations, nothing to worry about. It's just simple addition and subtraction of velocities and position. Okay, you're seeing a coordinate system in the board. It's blue in color. Okay, now suppose this is the coordinate system for you. This is how you visualize this 3D world according to your perspective. Okay, this is x, y, z. Okay, complete 3D perspective of yours, and you are right now at rest. Okay, now you can see that I'm constantly moving, going forward, going backwards, but I'm constantly moving according to you. Okay, So from your coordinate system, from your perspective, you will look at my coordinate system something like this. So my coordinate system is x prime, z prime and y prime. Okay, so this is my coordinate system according to you. Okay, now suppose I have a particle, suppose this chalk is the particle I have. Okay, now I have had some like pretty distance between it, a feet. Now let's suppose this feet, I take it as a distance here, it is p according to me. Okay, so according to me the coordinate systems of it will be like x prime, y prime, z prime, but the distance is mostly at x. So I can say that it's at a distance x prime relative to me at least. Okay, so but for you the distance would be slightly different. For you the distance would be a bigger one compared to mine. This is your distance, a total of x. Okay, now suppose I am moving at some particular velocity with respect to you. I am moving at a velocity which is uniform and is v. This is the uniform velocity of my reference frame. Okay, so we know that speed is distance is speed into time, so vt, and since t prime is equal to t, which you saw in the earlier video, it will be the same for you and the same for me. So now we're going to proceed in the next part. What is the distance between you and me if I keep on moving with the uniform velocity of v in time t? It will be vt. So this is distance, a unit of length. This is a unit of length and this is a unit of length. So you can conclude from this a formula which is x is equal to x prime plus vt. Okay, pretty fair and simple. This is one of the first equations of Galilean transformation. Now if you want to talk about the further ones, suppose you want to find the velocity, suppose you want to find the acceleration, then we are going to have to simply differentiate it one by one to x prime plus vt. Now we have to find the velocity, we have to find the acceleration, and that is just simple differentiation. Okay, adjusting that a bit, I can write it like x prime is equal to x minus vt. Now from here I need to find the velocity. How are we going to do that? Just simply differentiate with respect to time, dx by dt. Since this velocity is a uniform constant motion and hence it is a constant, I am not going to consider this inside the equation, but rather I am going to write it like this, dt by dt. Any of you are still confused about t prime equal to t, it's just t prime equal to t, so it's going to be same for both of us, no problem in that. Now from this I can conclude, you know, what is position with respect to time. Derivation, we can conclude that this is this, this is this, this is this. Bit of a fancy derivation. So it basically means this is the velocity of the particle with respect to my frame of reference. That's like how I see the velocity of the particle. This is the velocity of the particle which you see. Okay, and this is my velocity with respect to you, like how fast am I moving with respect to you, supposedly that you are at rest. So from here we can do another derivation of acceleration, which is basically just another derivative. Okay, it just goes to the second derivative of the position and the first derivative of the velocity. So this would become acceleration prime and this would become acceleration, but this time this v is a constant and it becomes a 0, and we end up till here, a prime is equal to a. Now this makes some sense since we are moving at a uniform velocity. So a prime is equal to a. That means if I am accelerating, which I am clearly not, you are also accelerating at the same rate. Okay, but this is only for inertial frames of reference, because till now we have only talked about inertial frames of reference. IFO means inertial frames of reference. But now we are going to talk about non-inertial frames of reference.